That's the last version. Actually, it was
Okay, so today we're going to talk about fronts. And the first question is, what is a front? Does anybody know what a front is? Right here?
Opposite of flag.
How would you define a front? In the atmosphere or in the ocean or anywhere that you...
It's something hot and cold.
Something hot and cold? A transition? But how hot and how cold? The transition from hot to cold. But so, does it need to be strong? How strong? I mean, what makes it a front? Well, like this, right? It's like pornography, right? Or like defining an estuary. Right? It's hard to define, but easy to see. As you can see, that there's a front right there. This in the Rio de la Plata in Argentina, and it's a photograph from a flotsam there, flotsam. And so usually, like AJ say, you can look at it in terms of change in temperature. What is it? A change of how many degrees in how many meters. What makes a front? So typically, a front will accumulate some sort of material at that transition. That is, a front is a region of convergence and divergence of flow. It can be in the air or in the water. And it was first used in meteorology and denotes a rapid change of properties, rapid change with respect to the surrounding or to the areas away from the front. So at the front you have enhanced gradients. That's really how you could define a front, an area of enhanced gradients with respect to the surroundings. And they're caused by physical processes. We're going to talk about surface fronts today only. As you can see in that picture also of this nice slick that is formed by different surface tension between the two water masses, and that change in surface tension is caused by the accumulation of material at the front. So in the ocean, we tend to see fronts at the surface, or surface fronts, because there is a mark, a line on the surface of the water, typically. There are fronts also underneath the surface, and many times you don't see them. Sometimes you can see them at the surface because they have a surface expression. They cause something at the surface. But every time you have a front at the surface, you're going to have some marker, flotsam or algae accumulating there, or trash accumulating there. So that's a good indicator of fronts. But so how do you study fronts quantitatively? Or how do you look at them from a dynamical point of view? So we're going to follow this paper by Jim O'Donnell back in 1993. He's updating it with recent findings on mixing processes, but essentially the basis of the concepts remains the same. So in order to study fronts, we use the buoyancy equation, or the density equation. That looks something like this. We have the local changes of buoyancy. B is the buoyancy, and we're going to call the buoyancy as a density anomaly. So the difference between the observed density and a reference density normalized by the reference density multiplied times gravity. So in a way, this is analogous to what? This buoyancy is analogous to, see, when we multiply a small quantity times gravity, it's the reduced gravity. So in this context, buoyancy is also a proxy for reduced gravity, or it's essentially the same thing as reduced gravity. So we're looking here at the local changes of reduced gravity, advective changes of reduced gravity, and then we have the divergence of the diffusive flux of buoyancy, and we have a source term for buoyancy. So this source of term for buoyancy can be, what can it be, you think? What would produce buoyancy in the ocean? Salinity. If you add salinity, it will cause buoyancy. Negative buoyancy. So what would cause buoyancy? What would cause a flood?
Temperature.
Freshwater input. That's right. Heat. A heat flux. Buoyancy river. A river input. Sorry. Rain. Any of those. So an addition of fresh water or an addition of heat. So that's what this term represents here. Notice that we express it as a function of space and time. All right, so we're looking at the advective changes of buoyancy, the diffusive changes and the sources of buoyancy. So notice that if going back to this definition of buoyancy, or this expression for buoyancy rather, if the observed density is greater than the reference density, this will be negative, so you have negative buoyancy. So you have an overturn of the water column. Right? So like you say, if there's evaporation, you're losing fresh water, salinity gets concentrated, then you're going to have an overturning. Or the same thing when you have a cooling pulse or a cooling event on top of the surface of the water. It'll cool it down, so it'll make it denser, it'll overturn. And on the other hand, if the observed density is smaller than the reference density, this numerator will be positive, so you have positive buoyancy. So whenever we have a smaller density than the reference density, that's what happens in fronts, right? That you have different densities. And the water mass with the lower density will override the water mass with a higher density. So that will cause stratification. So in order to see how fronts may evolve in time, that is, looking at this equation, we're going to look at the spatial changes of buoyancy with time. So we have to differentiate this equation with respect to space. So we're going to differentiate it with respect to x, but you can do it with respect to y also. At the end, you're going to get the same mechanisms that produce these changes. So what do you think this term represents here? What does that tell you in symbols? So in words, this term is representing what?
Y is in the direction of time.
Sorry, I didn't get it. I just heard time at the end. Because it was like in church, everybody was saying things. Not that I go to church, but anyway. But I've been.
As a change of buoyancy in the x direction with respect to time.
Very good. So what does the change of buoyancy in the x direction represent? So this is a horizontal gradient of buoyancy. So this will in essence represent a front. How will the horizontal gradient in buoyancy change with respect to time? And it'll change with respect to each one of these four mechanisms. So the first one, let's look and see if you can tell me, even though you have it there on your notes, what it represents. This thing in the in these brackets, it's an advection, right? An advection of a horizontal buoyancy gradient. So that's essentially what it represents. It moves the buoyancy back and forth. Or not back and forth, but over space. Now here, what do we have here? In here we have mixing and buoyancy, right? And we're looking at the spatial variations of mixing and buoyancy. We know that. Does that make sense? What's going to happen in the region of very sharp bathymetry changes? You're going to have areas of larger mixing maybe in the shallow parts relative to the deep parts. So that is contained in this. So that's a mechanism to form a front. If you have more mixing locally at one area relative to the other, then you're going to have mixing here but no mixing here. That will create a rapid change in buoyancy. So it'll enhance this term. Now, how about this term? Can everybody see anything in that term? Don't get distracted by the numbers that appear there. dVdx means what? A lateral shear. So the interaction of the lateral shear with a buoyancy gradient that's in the opposite direction, in the perpendicular direction to this. So again, and the last term involves convergence or divergence, right? And the changes of vertical velocity in the x direction. So I don't know if you can see that all of these terms come from differentiating this equation with respect to x. So this differentiating this one with respect to x gives us this one. This one with respect to x will give us two parts, right? This part, the first part, and the second part gives us this one and that term. And then the differentiation of these two terms together with respect to x gives us this term. So they're given here. Let's look at them again. So this first mechanism represents a change of the gradient by advection. Not a mechanism to form fronts, but just to advect them around, to move them around, to move the fronts around. Then the mechanism number 2, differential heating or mixing, and this will generate what's called tidal mixing fronts. And we're going to look at each one of these in detail. So this happens when vertical mixing dominates over buoyancy, because otherwise you will have mixing, and then you won't create a horizontal gradient. Then the third term represents the enhancement of a density gradient by differential advection in the presence of a density gradient in the perpendicular direction. So we'll look at the diagram of what this means later. And then the fourth, the one that involves convergences and divergences, is an enhancement of the density gradient in the presence of convergence and sinking, or a reduction of the density gradient in the presence of divergence and upwelling. Again, we're going to look at that. So these are called the plume fronts. And those are the ones that have been studied most. So those are the ones that we're going to talk about first. So you have here the plume of, what river is it? It's the largest river in the U.S. Yeah. Is it? Is it the largest river in the U.S.? Which is large?
Amazon is the largest river.
In the U.S. Yeah, it is. It's this one or the Columbia, but the Columbia is very seasonal, strongly seasonal. So it is the Mississippi. And so you see here the plume of sediments. Those of you who love sediments, you have the plume of sediments there from both the Mississippi and the Atchafalaya River that comes out here. And this is a photograph. You can see very clearly the plume. And usually these plume fronts constitute a thin layer from the riverine water. Sometimes the salinity contrast is up to 10 between the ambient water and the plume water. So there's a picture of a plume. This is in the Chesapeake, outside the Chesapeake Bay, south of the Chesapeake Bay. Some of you might know that this is the Dock Army Corps of Engineers pier, and so this is the plume of the Chesapeake Bay waters expanding southward. So you can see very clearly there the plume front. And here are some examples of what a plume front looks like. So here we have, look here, it's the depth, only 3 meters deep. Obviously the water column goes further down, maybe to 15, 20 meters in this area. This is in Long Island Sound. This is the Connecticut River plume that comes into Long Island Sound. These are the upper 2 meters, and look at the scales in the horizontal. We have 160 meters only here. And these are contours of salinity. This is 5, 10, 15, 20. And notice the sharp change. This is 25. Actually, this is 30. 30, and this is like 32 or 33. So notice the very dramatic change. And this is shown here at the surface salinity. This is the surface salinity. Goes from 25 to 5 over a distance of what would you say? So it's a change of 20 salinity units over what distance? Yeah, around 5 meters. So can you imagine measuring this? You have to be very, very careful, because look at the depth. Underneath 2 meters, you don't see the plume anymore. Underneath 2 meters. And also the horizontal scales. In 5 meters, you're going to smear out the anatomy of the front if you don't sample very quickly, like here, right? It's very dramatic. The change of salinity is quite dramatic. And then together with the salinity field that's shown here, this is the flow field, and this is flow going in that direction at around 50 centimeters per second, and this is flow going in the opposite direction, or it's practically stagnant at 15 centimeters per second. So you can also see a very sharp gradients in the flow too. So what do you think? What's the order of magnitude of the vertical velocities associated with this front? But first of all, right here at the front, the vertical velocities would be downward here, so the heavy water would sink, and then you'd have sort of a roller here at this front, going up like this. So right here, if you were able to measure the downward velocities at the front, the plunging of the heavy water underneath the plume, how fast do you think that would be if you don't look, without looking at your notes? Just from what you might imagine, how strong would vertical velocities be? Say when we've been on the field, have you seen the water moving upward or downward? Maybe, if there are eddies, right? But usually you don't see water going up and down. So typically the vertical velocities are rather small. How about at these fronts? I don't know if you've observed what goes on right there, right at the interface. And we didn't have fronts really to talk about during our 2 field trips that we could see from the surface. There was a signal in Ponce de Leon in the trace of surface and temperature that we measured, but it was not obvious, I think, from what I remember. Is that true? Okay, so going back to the question, how strong do you think these vertical velocities are? How many? Half a centimeter per second? Or half a meter per second? Half a meter per second? Okay. Does that sound reasonable? Half a meter per second? Just to give you an idea, in an upwelling region, that is when the wind blows offshore, and that causes the bottom waters to come up to the surface. The strongest velocities are on the order of 10 to the minus 4 meters per second. So that's 0.01 millimeters per second. 0.01 millimeters per second. In the canyons, I don't know if you were at Amy's talk on Monday, but those vertical velocities are also, at the most, they're 0.1 millimeters per second. 0.1 millimeters per second. Right? So here at the front, actually Thai is close to the value, but it's really 10 centimeters per second. Half a meter per second, imagine a vertical velocity of half a meter per second. If it's downward, it's going to suck you in and drown you. Like half a meter per second. It's going to suck you down in. So these are around 10 centimeters per second at the most. And how can we see that? We can look at or verify a value like this of 10 centimeters per second just by looking at the vertical profiles of the ADCP that measure this section. So what you have here is the time average profile, that's a green line, of the vertical velocity throughout this entire region of the plume. So if you look at the vertical average is essentially zero, or very weak vertical velocity. This is the standard deviation, the gray region. But right here at the front, they set, so maybe all these profiles that you see next to each other, bunched up in distance. You see, the green line shows you what values. These are centimeters per second. So on the order of 10 centimeters per second, right? And you see the standard deviation. Now when this guy Jim O'Donnell made these observations back in the mid-90s, he said, these are too large for vertical velocities. Can I trust these measurements from the ADCP? And what he did was looked at the conservation of mass at the front. And by looking at the conservation of mass, you can calculate the rates of convergence, dV dy, assuming that there's no convergence along the front, or the flows perpendicular to the front. And he found out that in 15 meters, over a distance of 50 meters, he observed a velocity difference of 65 centimeters per second. So around 50 going one way. It's as if saying 50 going in one way, 15 going the opposite way. So that's 65 centimeters per second in 15 meters. So that gives you a convergence rate, a large convergence rate that you can integrate. So this would be the continuity or conservation of mass. You can integrate the dV dy over the 2 meter deep plume, and what you get is 8 centimeters per second. So from the order of magnitude estimate, he thought that was reasonable. And subsequent measurements by other people have shown that yes, you can observe that very large vertical velocities. And also, as a reference, when you go to the springs here, the springs that surround our area, I don't know if you've gone and see how the jet coming up. I said those jets have on the order of 20 centimeters per second. That's the speed of the water coming up. That was that we measured, and it was low flow. So probably when the aquifers are charged, those jets are stronger. Okay, so but these plumes are generally delimited by a narrow zone, as we said, of high horizontal density gradient, and that's why you see here the foam line and also the change of color. So this is turbid water. This is from the Rio de la Plata estuary in Argentina. So this is waters. Which one would be waters from the river, you think? This one or this one? The dirty water, the turbid water. And when these plume fronts occur instead of outside the estuary, like in this case, a plume front would occur here. The cousin of these plume fronts are what's called the tidal intrusion front. So the plume fronts tend to be more evident during the ebb phase of the tidal cycle. But then you can have a tidal intrusion front, which is the same mechanism. You have very strong convergences and divergences here at the front. I don't know if you can see the V-shape of the tidal intrusion front here on the photograph. And it's outlined there. And there's a better photograph yet of that tidal intrusion front. So which one, by looking at that, which one do you think is lighter water and heavier water? Probably here is evident, right? I mean, you could see the turbidity of the water, right? And besides, I mentioned that these develop during flood period, so you have cleaner water coming in. So given that, you can easily see which one is the ocean water and which one is the estuarine water. So you have the estuarine water here and the oceanic water here. Very interestingly, though, notice the shape of these tidal intrusion fronts. They tend to form this wedge or V shape, and at the tip of the V shape, you tend to have these neat eddies. I'm going to show you another example, two more examples of these tidal intrusion fronts of what they look like. This example we've used before. This is a time series of depth versus time of the tidal intrusion front at the James River estuary. And you can see here during flood the high density water intruding here. There's a front right here. So this is the bottom expression of that tidal intrusion front. So the surface expression does not appear on this figure. It developed later on. But so this illustrates the large phase difference between the surface intrusion front and the bottom intrusion. So in those photographs, if we go back, this surface expression of the tidal intrusion front means that near the bottom, the salt wedge is probably further upstream. Same here, the salt wedge is further upstream. So there's slanting like that, these fronts. And also another example of this comes from another one that I've used before, here from a glacial fjord. And there's a very shallow seal here. So during flood, you get the nice and clean waters from the Strait of Magellan, meeting the milky waters from the glacier that are here. You can even see it here on this photograph, how this water is sort of milky and this water is darker. So you can see the dramatic difference in color, and very nice front there. You can see how if you don't sample these features very finely, you miss them easily. And in this case, this would be what waters from the ocean or from the glacier? From the glacier, right? It's obvious. And these are, and see all the small scale eddies that form at the front. And looking at it from a different perspective, that V-shaped wedge is right here, and it's accumulating ice right there at the wedge. You see how the front is undulating like that? So this is the view from the other side. The oceanic water is moving that way, and this glacier water is sort of stagnant there. So this water, what's going to happen to this water when it meets the glacier water? It plunges, right? It's a very dramatic plunge. And it is very dramatic. When you sit on top of it, you actually can see the plunging. It's quite a spectacle. And you see these eddies. Yes?
Is the the point, does it form at any certain location, like channel or anything in the estuary, or is it in the wider?
Pretty much in the middle. So yes, actually not in the region of in the deepest part, where the water can intrude further. So it has to do with the bathymetry, where the large V shape. So this is a smaller scale feature. And in the UK estuaries, that V wedge tends to be in the middle, because many of the estuaries have a sort of a nice cross section of the bathymetry, a U shape. So usually the deepest part there is in the middle. In the case of the James River intrusion front, it tends to be biased toward where the deep channel is, so a little bit to the north in that particular position. And also, I mean, in addition to the beauty of just the simple beauty of these fronts, they have tremendous ecological implications, because they tend to accumulate organic material. And in this case, we could see, I think I've mentioned this before, we could see small shrimp, so euphausids, being right there at the surface, being swept in because they like to be near the bottom, away from the surface, because they know that when they're near the surface, they come to the surface only at night to eat those euphausids. So during the day, they don't want to come up, because they're large enough, so in such a way that the birds can see them and the fish can see them, and they're gone. So in this case, they're swept up by the flow over the seal. That's a Bernoulli suction. So that when the flow accelerates over the seal, it suctions the water from underneath, say from depths of 60, 70 meters, suctions the waters back up to the surface. So the birds were having a feast there when we were able to see these euphausids at the surface. Because also, it's not only the birds feeding the euphausids directly, but fish, a lot of fish congregate there. So again, the birds were happy. Okay, there's another view there. And again, looking at that very nice wedge that is accumulating a lot of the ice that was discharged during the ebb. So during the ebb, you get mixing both, but during the ebb, then you have something that looks like a plume front, and this is seaward of the shallow part of the seal, and you can see how the glacier water forms a convergence line here. And again, you see a lot of organic material accumulating there at the front, in addition to the ice. So the ice is a nice indicator of the front. All right. We can say many things about the plume dynamics just on the basis of its shape. And in order to characterize the shape, we can look at how long it is and how wide it is. We'll call it how long it is by L, capital L, and how wide it is by this product of gamma L, where gamma will be called the slenderness parameter of the plume. This is based on a work by Garvine in 1995. So notice that the smaller this slender parameter, the longer the discharge, like in this case of the Chesapeake Bay plume outflow. It forms a nice coastal current here. And the larger this gamma, the more radial the plume will be. So if gamma is large, instead of the plume being elongated like that, it'll be just like a bulge, a radial bulge. So with that, we can know something about the dynamics. How would you say? Well, you can look at different systems. And this is a busy table, but I'm going to ask you just to concentrate in those two columns. You have different plumes there. And these two columns show the Kelvin number and the fruit number for those plumes. Do you remember? The Kelvin number equals this L represents how wide the discharge is versus the internal Rossby radius. Do you remember the internal Rossby radius equals what? I haven't asked you about your morning sayings for a long time, but this involves that. The internal Rossby radius is part of your morning sayings divided by Coriolis parameter, right? Square root of G prime H, the speed of the internal gravity, long internal wave, G prime H, divided by F, the Coriolis parameters. That's what the internal radius of deformation is, this one. So you can think, remember the Kelvin number, if the Kelvin number is larger than 1, it means that the discharge is greater than the internal Rossby radius. So what that means is that within that length scale you have a geostrophic balance, the internal radius of deformation. When you have a Kelvin number that's very small, it means that the discharge has a small scale of discharge, that it doesn't even span an internal Rossby radius. That's when the Kelvin number is small. Right. And then the Fruit number. What's the Fruit number there? What does that represent, U and C? And you were at Amy's talk also, she talked about the Fruit number. Or maybe you didn't know what she was talking about. So what's that? No? You don't want to say anything today? You want me to do all the talking today? So that's the flow, maybe the flow at the plume, the flow that you observe. And this C, what's the C? It says GH or G prime H. We're talking a stratified flow, so it's G prime H, square root of G prime H, the long internal wave, the speed of the long internal wave. So you can see that. So let me go back. For a low Kelvin number, it means that you don't have the scales for an internal Rossby radius to fit in those scales. So it means that the flow is not geostrophic. It's away from geostrophic balance. So you can see that for a large Kelvin number, you have several internal Rossby radius in the scale of that discharge. So it means that the plume may be in geostrophic balance. So that's a good diagnostic for a geostrophic balance. Now the Fruit number, what does it tell you about how inertial the flow is, whether it's supercritical with respect to a long internal wave or not? So if it's supercritical, it means that advection is important, right? So if the Fruit number is large, it means that advection is important. If it's small, it means that advection is not important. And if you look at the two columns, the small Fruit numbers correspond to high Kelvin numbers. So it means that there's less advection, and the dynamics is practically controlled by geostrophy, that is pressure gradient balanced by Coriolis. Whereas in the upper examples, you have relatively large Fruit numbers and low Kelvin numbers, meaning that advection will be important in those plumes. So in essence, for low Kelvin number and high Fruit number, Garvin called these plumes inertial plumes, and those are the small scale radial plumes. And for the ones with high Kelvin number and low Fruit number, those are the long discharges, like the Chesapeake Bay, and those are said to be in semi-geostrophic dynamics, because the dynamics across the direction of propagation of the plume or of the coastal current is geostrophic. So let's look at a couple of pictures here and see if you can guess where we're. So this is one of these actually. This is one of these, and so the scale here is probably around 5 kilometers across here. So the coastline is this, and you have a relatively warm water being discharged here from a treatment plant, relatively warm water, and you can see the shape of the plume is like that. You see the shape of the plume, more or less? So given that shape and the scales, what kind of plume would you say it is? Is it a large-scale plume or a small-scale plume? It's a small-scale plume. It's an inertial plume. So it's going out radially. It's a little slanted, as you see, toward the left, and that's perhaps because of wind or a coastal current around here. So this is in the Niagara Lake, and this is the Point Beach discharge. And so you can see also that the Mississippi River discharge and the Amazon River discharge. Sorry, this example is from the Niagara. Point Beach is from another treatment plant analogous to this one. So these 1, 2, 3, 4 examples, they're all inertial plumes. And they don't respond very well to the effects of the Earth's rotation. If you've looked at the Amazon plume and the Mississippi plume, river plume, they're both affected by the local current. If the wind is blowing in the sense opposite to where the Earth's rotation should take this plume, it'll take the wind-driven flow will take the plume with it. So what this means to the dynamics is that the inertial plumes are not reactive to the effects of the Earth's rotation, as seen here by the Kelvin number and by the Froude number. In contrast, the large discharge plumes, like this one, where is this? You can get a hint from what it says here. Yeah, that's right, British Columbia. You should have identified that immediately. So this is British Columbia. If that's British Columbia, this is what? Alaska. So this is a picture of surface temperature, and you see here, this is the Alaska coastal current. And you see the length scale of this. This is thousands of kilometers. Thousands? Well, at least several hundred of kilometers here. And the width is much smaller than the length scale. So this is a slender plume, long plume, and actually here it is. It has a Kelvin number of 1 and a Froude number of 0.3, so it's a semi-geostrophic plume. The same thing can be said by all these plumes, the Rhine, the Delaware, the South Atlantic Bight. So all the river discharge here in the South Atlantic Bight, in South Carolina, Georgia, you see that we have a lot of rivers there that discharge the fresh water. All that fresh water turns to the right with Coriolis and forms a coastal current, whose offshore scale is much smaller than the alongshore scale. So in this type of plumes, the alongshore scales are much longer than the crossshore scale. In these types of plumes, the alongshore scale is approximately the same as the offshore scale, the radial plumes. Okay, so now let's talk about the mixing fronts. And these are like the ones that we mentioned before when we talked about the competition between mixing and stratification. So they develop over regions of sharp bathymetry change, and if you have strong tidal currents in this area, those strong tidal currents will mix the water column here and will leave this area stratified, so you get a mixing front right here. And so that depends, the position of the front depends on the ratio of H over U cubed. That's the main idea of this. And hopefully you can see this. Oh yes, you can. Good. This is a simulation, a numerical simulation in Georges Bank. Georges Bank is here. So that's the Gulf of Maine. There's Nova Scotia, Canada. There's Cape Cod. So Georges Bank is right here. And this is Georges Bank. It's a simulation. This is the temperature field, and this is a phytoplankton field. So if we go back, let's go back. No, it'll start again. So initially, it's all stratified here. I don't know if I'm going to be able to stop it. I won't be able to stop it. But look at the chlorophyll is also stratified. So then when the tidal currents start acting, look how they are effectively mixing the water column. Whereas outside of the bank, the water column remains stratified, both for temperature and for chlorophyll. Very neat here are these waves that are generated from the interaction of the tidal flow with the bathymetry, with the sharp bathymetry chains. You see those? Look at those waves. They're very nice. You can see them in chlorophyll also. So again, this area is well mixed, whereas you have stratification here. So you have a well-defined front right there and right there. You see the fronts? And you see them both in temperature and in chlorophyll. So those are the tidal mixing fronts. Then we have the shear fronts. And these are also very neat. You can see these in St. Augustine Inlet. And I'm sure we'll be able to see those in Ponce de Leon Inlet when there's some fresh water input there. So this results from the differential advection of fluid by tidal currents. By that we mean that the flow will be laterally sheared. The tidal flow can be laterally sheared because of bathymetry, right? So we have a channel. The tidal flow will be stronger over the channel than over the shoals, and that will create a lateral shear. So that lateral shear will strain the density field in that way. So then, right here at the edge between shallow and deep water, you're going to have an elongation of the density field that will create fronts that can be aligned with the bathymetry. So they look something like that, and probably you've seen them somewhere. They tend to be aligned with the bathymetry. So this is in the Chesapeake Bay, aligned with the main channel at the entrance. It's on the northern part of the entrance, and this is in the James River. You have this front that's accumulating, in addition to foam, it's accumulating trash. And so that's a way of representing this mechanism here. It's the lateral shear interacting with the horizontal gradient of buoyancy. Right. So this is the horizontal gradient of buoyancy in that direction, interacting with the lateral shear of the flow. Okay, so how did I say this? dBdx is the horizontal density gradient. That the density gradient would look something like this, right? High salinity here, like that. And then the lateral shear of the longitudinal flow will interact with that gradient to elongate, to strain the density field and favor the formation of these fronts. Schematically, this is what happens and what the explanation used by most people to explain this type of fronts. So we're looking now at a cross-section of an estuary. So this is depth and distance across. We're looking into the estuary. And by the end of flood, because of this differential advection mechanism, we're going to have higher salinity here in the channel relative to the shoals. That is, there's more advection of high salinity water here than here. So in such a way that by the end of flood, we have this density gradient, lateral density gradient. So that lateral density gradient, you have low salinity water here, will produce this lateral circulation like that, with convergence at the surface and divergence at depth. So you have a lot of references here that have used this mechanism to explain the convergence at the surface. And during ebb, by the end of ebb, you would have the opposite. You'd have more advection of low salinity water here than here, in such a way that by the end of ebb, you have low salinity water here and high salinity water on the shoals. So because you have low salinity water here, that would cause the water to move to the sides at the surface. Right? So that results in a divergence at the surface and convergence at depth. Now, that's the mechanism that has been used, but I'm not sure that that's really what happens. And again, this is something that's open for discussion, because this mechanism right here predicts that there are no fronts during M. And we have observed fronts during M in many places. I think I'm going to have to stop there because we've run out of time, but I'm going to leave you with that suspense. So we'll come back to talk about, because I don't want to rush through this part, because it's a topic of discussion. I've already, well, let me stop this first.